Welcome to a lesson with Dr. Powell. Let's take a look at how we can find a basis for an orthogonal complement to a subspace. See this vector space V, we're going to think of it as a subspace of R3. And we're going to do this using reduced row echelon form, actually. So what we're going to do is we think about this, this vector space, which is spanned by these two vectors. And we can think of those two vectors as rows. Find the reduced row echelon form, which in this case can be done in one step. An airdrop up this way by multiplying this row by a -1 and adding it to that one. And we arrive at 1, 0, 1, 0, 1, 1. Okay, now all we need to do is find the kernel of this reduced row echelon form, which in a previous video in my playlist, I showed how we can do that from reduced row echelon form in a quick way. What we do is we identify non-pivot columns, and then we extend all the columns down so that they have, since we have 3 columns total, we want 3 in each column, so it looks kind of like a 3 by 3 matrix, a square matrix. Next, we go to each pivot. So as each pivot comes across and changes the things that it hits as it goes. Like this one, it's in column 1. So when it hits something, as it moves across, it'll move whatever it hits to row 1. Well, that just stays in the same place. In fact, if they're backed up here, it doesn't move it. So that's nice. But it not only keeps it there, but when it sends it to where it currently is, we have to change the sign. So this one would become a -1. This one, coming from this pivot, would change to a -1. It stays in the second row since this guy is in the second column. And then lastly, we think about like adding 1s down the diagonal, and we would be adding a 1 down here. So it looks like we have -1, comma, -1, comma 1. And this right here should be a vector that's orthogonal to the subspace V. In fact, it's a basis for the orthogonal complement of V. So the subspace of all vectors that are orthogonal to everything that's in V. And you can even see this by checking. You can take this vector right here and dot it with either of these and notice that you'll get 0. We take the dot product of two vectors and you get 0, that means they're orthogonal. Okay, so we take a dot product and we end up getting -1 plus -1 plus 2, which is equal to 0. So that one looks good. Then we can check the other one. 0, 1, 1. And sure enough, as we do this, notice we get 0 plus -1 plus 1, which is 0. So we have successfully been able to find that. Okay. Let's now use the same technique to find a basis for the orthogonal complement of the span of this vector right here, 1, 1, 2. Okay, so how would we do that? It's the same idea. So we think about, well, it's just one vector. We think of it as a row. It's already even in reduced row echelon form. So we use our column technique. A square matrix, and as this comes along, it keeps these in the same position, so that's a -. Then we just put 1s down the diagonal, adding to these non-pivot columns. And there are 2 vectors that span this space that's orthogonal to that vector. So, so what we get is 1, 1, 2, the orthogonal complement of this is equal to the span of the vectors -1, 1, 0, and -2, 0, 1. Okay. So, and you can double check it if you take a dot product of this. With that, that's 0. That with this one, it's also 0. So we're good. Thanks for watching.